Hello, today I will be presenting cryptography and modular arithmetic, the RSA algorithm. My name is Mario Jurado and I'm going to present this for my class of discrete math. I will be presenting an overview of the RSA algorithm, one of the most widely used methods for securing digital communications. This presentation will cover how RSA works, from selecting prime numbers to encrypting and decrypting messages, and I will explain the mathematical concepts involved, walk through step-by-step calculations, and showcase how they are implemented in Python code. First of all, I will start explaining what is cryptography. Cryptography is the science of protecting information by transforming it into unreadable formats using mathematical principles. It ensures that only authorized parties can access to the original information, preserving confidentiality, integrity of the information, and authenticity. Now I will explain why modular arithmetic is important. Modular arithmetic is essential for the cryptographic algorithms because it allowed to large numbers to be reduced into manageable values using modular arithmetic. RSA in particular use modular arithmetics to securely encrypt and decrypt data without exposing the original keys. Why is RSA significant? RSA, that are just stands for River Shamir Adelman, is one of the most widely used cryptographic methods. It allows to secure data transmission even if the encryption method is public, relying on the difficulty of factoring large numbers. In real-world applications, we can see that applications that use communications, sometimes they tell you that they use end-to-end encryption. This is a most commonly way to tell that the application is using RSA and modular arithmetic to encrypt the data that you are sending to other persons. Also, modular arithmetic is really connected to financial transactions and many other applications. As project objectives, I have understood the role of modular arithmetic in RSA encryption. Also demonstrate how RSA secures data transmission using real-world examples, and also develop a fundamental knowledge of cryptography for future applications in cybersecurity. Understanding modular arithmetics. What is modular arithmetics? Modular arithmetics involves warping around numbers after reaching a certain value that is commonly known as a modulus. It's a kind to how a clock works when one reaches 12, it resets its count. So why modular arithmetic is important in RSA? RSA operations require very large numbers. Without modular arithmetic, calculations will be computationally expensive and also impractical. Modular arithmetic keeps numbers manageable by working with reminders. Here we can see an example calculation from 14 mod 5 equals to 4. Now we have to calculate n and phi of n. To start building RSA algorithms, the first step is selecting two prime numbers, which we are going to call p and q. For this example, we pick small numbers that are p for 53 and q for 61. One of the conditions is that both numbers have to be prime numbers. Usually, the algorithm that encryption for like applications like WhatsApp use like really large numbers as prime numbers that makes them really complex to computate and to decipherate and to factorize. So for my example, I use small numbers. In once we have P and Q, we calculate N. N is a modulus that will be used in both public and private key during the encryption and decryption process. The formula to compute N is straightforward. It's N it's equal to P multiplied by Q. So multiplying 53 and 61, we get 3 3,233. This value n is essential component for the RSA keys and needs to be publicly shared. The next step is calculating phi of n, which is also known as Euler's totient function. Basically, we just need to take P and Q and subtract 1 from each number, and the result of that new multiplication, it's going to be phi of n, that in this case it's 3120. So summarizing, we now have two key values, and it's 3233, and phi of n is 3120, which is used in calculating the encrypting key E, and it's corresponding to the private key D. These calculations are foundational in the RSA process, and they enable the subsequent steps of the algorithm, including choosing a valid encryptation key and generating the private key. To help demonstrating this visually, I include a code snippet showing how these values are calculated in Python. The output of the code confirms our manual calculations that, to be honest, I just did in Python because it will be really slow to do real calculations. These numbers are small, but the real RSA algorithms that are usually professionally have really large numbers, so it will be really difficult to me make the calculation manually, and I can just make code to do it for me. Okay, now that we have our modulus n and phi of n, we need to choose an appropriate public exponent denoted as an e. This step is crucial because e is part of the public key and will be used for the encryptation message. How to choose e? The public exponent e must meet the following criteria. It must be an integer such that it's greater than 1 but smaller than phi of n. So it must be coprime to phi of n, meaning that the greatest common divisor of e and phi of n must be 1. This requirement ensures that e has an inverse modulo, which is essential for the decryptation process. Commonly choices for E are like E17, but I found that widely chosen value for E is 65,537. I'm not really sure why, but just for practical purposes, I chose E equal to 17. Here in this slide, I attach a table who show us which are the valid and invalid values for E, which also I did a little function in Python, a little script in Python to calculate the numbers that fit on that criteria. Here is the code example that I use to verify that the chosen E meet the conditions that we use. So we use the great common divisor function from Python's math module to check if the great common divisor from E and phi of n is equal to 1. Okay, now that we have chosen our public exponent E, we need to calculate the private exponent. This value is a crucial part of the private key and allows us to decrypt the message that were encrypted with E. What is D? Basically, the private exponent D is a modular inverse of the model phi of n. In mathematical terms, D satisfies the equation E times D equivalent to 1 mod phi of n. This means that when E is multiplied by D, the result when divided by phi of n leaves a remainder of 1. So here we have the calculation that can be done manually, but also I did a code in Python to automatize this task. Now that we have our public key components E and N, let's explore how the RSA encryptation process works. How does the RSA encryptation works? The purpose of encryptation is to convert a plain text message into a ciphertext that can only be decrypted using the corresponding private key. The encryptation process follows the mathematical formula M times E mod the N. Here, M is the numerical representation of the plain text message, E is the public exponent, N is the modulus, and C is the ciphertext. So basically it's the encrypted message. Okay, here we have an example. Let's encrypt the message hello using the E equals to 17 and the N equals to 3233. To convert each character, first of all, we have to convert each character to the ASCII language. So H corresponds to 72, E corresponds to 69, L corresponds to 76, and so and so. So we have to encrypt each letter in ASCII value using and then using the formula C is equal to M exponent E mod N. For H, the value is 72 exponent 17 mod, and in the mod we use the N, that is 3233, giving us a value of 3000. Here you can see the calculations for each letter. So at the end, our message it's going to become an encrypted sequence that it's going to be the one that is shown in the below part of the presentation. Now that we have encrypted our message hello into a secure ciphertext, let's dive into how the RSA decryption process works. Decryption is the reverse of encryption. Using the private key D and the modulus N, the ciphertext is converted back into the original plain text. The decryption formula is M equal to C elevated to D mod N. Here, C is the ciphertext, D is the private exponent, N is the modulus, and M is the decrypted numerical value which corresponds to the original plain text. Let's decrypt the ciphertext. We already have encrypted before the hello text. So basically using the D and the N that we have, we can apply the formula to decrypt the text. As you can see in this example, you have to use the formula to get the ASCII values of the encrypted message, and with that you can translate the ASCII values into the original characters. Combine the results to get the original message will give you the word hello again. This decryption ensures that only someone with the private key can reverse the ciphertext back into the original message. This step completes the secure communication cycle of RSA. Here is the code example that we use it to encrypt, decrypt, and then show us the message. As we conclude the technical explanation of RSA algorithms, let's take a step back and assess its strengths and limitations. Basically, its strength is that it's part from its mathematical robustness. The security of RSA relies on the difficulty of factorized large numbers. Even modern computing, this remains a challenge problem of for sufficiently large keys. Also, the public key infrastructure enables secure communication without requiring both parties to share a secret key. Instead, one party uses the public key to encrypt, and the other uses the private key to decrypt. And for the real-world applications, we have that it's widely used in security online transactions, encrypting sensitive communications, and authenticating identities through digital signatures. But also it has limitations like its performance. RSA encryption and decryption evolve exponentially with its computationally expensive. For large-scale systems, this can slow down the operations. Also, the key size matters. Small key sizes, that the one that I use in my example, are vulnerable to brute force attack. Modern standards recommend at least 248-bit keys, which increase security but demands more computational power. Private key security. Also, the strength of the RSA depends heavily on the secrecy of the private key. If the private key is compromised, the entire system is at risk. So basically, it's really useful and really secure, but also it depends a lot on how it is designed. In conclusion, I want to mention three main points. Basically, RSA use prime numbers and modular arithmetics to secure communication. This is the part that is really involved with discrete math. It also ensures the data confidentiality and authenticity in digital applications. And while quantum computations poses future challenge for the RSA algorithm, with today's technology is still one of the more secure and useful algorithms because of how hard it's for normal computers to use brute force to decrypt the messages. So basically, RSA it's a powerful encryption tool that secures digital communications using prime numbers and modular arithmetics. It provides a confidentiality and authenticity essentially for the secure online transactions and other applications as web message applications. While advances like quantum computing challenge the current encryption methods, RSA remains a cornerstone of the digital security. And with nothing more to say, thank you so much for your attention.